epsilon of n is equal to the error is epsilon of n is equal to the d of n minus y of n. So I have an error. Okay. And I want to minimize this error. I want to minimize this error. But now, because everything is random, and I can only characterize them through some probability density function, or like autocorrelation function. So we wish now to minimize error. So the objective now goal is to minimize the mean square error. So it is mean square error, and we define that. Okay, so some function mean square error is equal to. So if this could be a fixed or could be a random variable, but this obviously is a random variable, right? Because I take a random input, get a random output. So this is a random variable. And if I have a random variable, I really cannot find a single number. Well, it's a random variable, so I have to do it on average. In mean. So in the mean, I do wish that the mean square error is, and okay, another thing here, because it's expectation. So y stands stationary, y stands stationary. So the mean actually doesn't depend on n. So okay, all in all, I want to minimize these expectations of epsilon square n. I want to minimize. That is the mean square error. So this is expectation. I take the expectation. So okay, let me put it up. Okay, I have this desired output. So this is desired output. Desired output. I have a signal which is I can only model them using some random process. And I got the outputs and I get an error with the random. So now I want to minimize this. So that means in the average, this is the best thing I can hope for. Minimize the mean square error. Okay, is that understandable? Okay. So that is the goal of this. Now, and the question we need to find out now is find out those numbers. This is a fixed number. Okay. So to do that, we're going to do now is to take the expectation of this and treat this as an unknown level solve, and we're going to solve an optimization problem. Okay. All right. So that's the framework. Now, this thing described in the lecture notes, in the textbook, but because we rushing, a little bit. So yes, last night I read through the lecture note. I realized that it contained some typos. So I hope you can take some note of my lecture here and compare that with the note we have, because I warn you that some in the lecture note have some typos. So I apologize for that. All right. So let's see. First, so that is the definition here. Okay. Now, but first I can write this thing here as a simple filter. So I can write y of n is equal to summation in h k and x of n minus k. X of n minus k. And here k go from 0 to n minus 1. Okay. Now to make this thing easy to analyze, I'm going to turn this now into vector. So now I'm going to define. So maybe you can see this convolution here, what it looks like. So if you think about it, what you have here is the signal. Think again, the signal here. Here the signal, here the signal, and here's the x, signal x. And I take the signal x way that way. So here is n minus 1 to n minus n plus 1. And so on. And now I take the output. So here is y. And here is the signal n I need to compute in that formula. So this filtering operation, the convolutions, we know that it's having this, what it is really like, I put the filter. Here is the filter. Here is a filter H. And we just simply put the filter. Here is H0, 1, 2, and n minus 1. Right? So this is the concept of convolution. And I put this and I take the multiplication across there. And I sum them up. I got this. Right? So I multiply 2, and then I take the sum, and that gives me this signal. So that's how we do the filtering. And for the next sample n, I just simply slide this thing here along and slide more. Right? Okay, so that's the convolution. Can anyone visualize that? Okay. And because of that, I want to come back to the concept of the inner product and the vector. So now we define that I'm going to define the vector h is equal to the vector of h0 to h n minus 1. So this is the vector of all the filter coefficients. And the vector x of n is equal to x of n and x of n minus n plus 1. So that n is this vector, the column vector. And xn is a column vector, a window of x that I use to compute y at n. Okay, you see that? In that case, then I can write now y of n just simply equal to, so y of n is single scalar, and that is equal to x h vector here, taking the transpose, times x of n vector. Can everybody see that? Right? This is just simply all equal to the inner product of h and x of n. Right? So the conclusion